And we are now ready to move to the second speaker of the session, which is Ben Weider from MIT and Northeastern, and he's going to be talking about axionic band topology and beyond in Weyl charge density waves.
Thank you, Jen. Okay, great.
Good.
We're all good? Good, okay. So thank you again, everyone who's watching. It's great to be here. It's great to be here in person. I'd just like to add, it's the first time I missed March meeting, I think. So today I'm going to talk about how you can realize a kind of axion-like physics in theoretical models and potentially real materials of Weyl semimetals that become gapped by charge density waves. And I'm going to highlight our work on the material tantalum selenide iodide. The work in this talk derives from these three papers. Oh, what's the laser pointer? Okay, I don't want to hit you in the face, but very good. Okay. NAS does not show up. Okay. So I'll use the pointer, and if you have questions, just ask what I'm pointing to. It's a big screen. So anyway, this talk is derived from these three papers that are online, and this other paper, which should be online very, very shortly. So this talk is structured as follows. First, I'm going to briefly introduce charge density waves, and then I'm going to move on to discussing axion electrodynamics in condensed matter systems. And from there, I'll lead into the original proposal of what you might see if you have Weyl points that become linked and gapped by a charge density wave. I'm going to then move on to our research, namely our discovery of Weyl semimetals and charge density wave state in tantalum selenide iodide, or a recognition of the link between the Weyl semimetal phase and the charge density wave state in this material. Namely that above room temperature, it is a Weyl semimetal, and just below room temperature, it realizes a gapped charge density wave state. And then I'm going to move back to theoretical models of Weyl charge density waves in the mean field, highlighting under what situations you would see something that you might call axionic, and maybe some distinctions between that and things that people call axion insulators. And then at the end, I'm going to briefly discuss what happens if you add more Weyl points and higher symmetry to the system. So to begin, a crystal without some charge density wave can be considered something, an object with periodic lattice translations, and the charge density is also periodic with respect to some set of lattice constants A. If you induce charge order, then the charge density has a lowered symmetry. Other symmetries may also be broken, like time reversal, as Titus discussed, or crystal symmetries. And you could model this charge density wave in the simplest example for a unidirectional charge density wave as some additional term in the charge order that's some modulation with a strength delta, some wave vector q, and a phase angle phi. And this phase angle roughly indicates the position in real space where you'll have regions of high charge density. And so I'm not going to discuss too much the origin of charge density waves, but what I do want to say is this simple picture where you have pieces of the Fermi surface that are linked by q vectors does not really lead to relatively realistic predictions of susceptibilities to charge order in 3D. The real picture is very complicated, and you have to take other interactions into account, like the phonon spectrum or electron-phonon coupling. And so a good place to begin is actually in one dimension, and to discuss or revisit the story in polyacetylene. So polyacetylene is a material that can be modeled as a series of 1D chains, and the limit that you're considering one chain, it's just this half-filled chain of zigzagging carbon atoms, or trans-polyacetylene. And so this material is half-filled, and you would expect it to dimerize and open a gap. But when Heeger, Shirakawa, and McDermott measured the conductivity, especially in the presence of dopants, they found it to be highly conductive. And in fact, dopants could control the conductivity by 11 orders of magnitude. This netted them the Nobel Prize in Chemistry in 2000. And in fact, this Nobel was, prior to the Nobel in 2016, one of the first Nobels for some physics that had a topological origin, or a topological electronic origin. And to see the role of topology here, what you can do is think of the Sushri-Verheeger model of polyacetylene as modeling this dimerization as putting on a 2kF charge density wave with some additional phase factor phi. But if you imagine the system to have some additional symmetry, like spatial inversion, then the phase angle phi is pinned to one of two values, 0 or pi. And so you can consider this phase angle, as I said, to be the region in real space of high charge density. So with phi equals 0, you have a double bond on the left, and that corresponds to having excess charges localized on what is called the 1a Wyckoff position of the SSH unit cell. And you can also have a second phase where phi equals pi, and the double bond is localized on the right, and the charge is therefore localized at the 1b position. Now, if you compute the polarization of the occupied states in both phases, taken per spin, since the system is weakly spin orbit coupled, we can do that without too many issues. What I'll find is that these two states are topologically distinct, at least when measured by the polarization. So this is a polarization of 0, and this is a polarization of E over 2 mod E per spin. And so these two phases are still topologically distinct, even though they're just trivial atomic limits that are related by a mirror and a fractional translation. And so you and I might disagree on which phase is topological, because none is more topological than the other. However, what we will not disagree on is that if you make a domain wall between the two phases, a topological soliton will be bound there, and this soliton can emit a charged state, and so these solitons can be one explanation for the conductivity. You can put in defects, they bind charged solitons, or dopants, they bind charged solitons, and then under a sufficiently high electric field, they begin to slide, and they act as charge carriers. Now, it's additionally worth noting that in this picture, I'm only considering the electronic orbitals. So the net charge of the system is not 0, and the dipole moment, which is essentially what the polarization is, this formula, can be shifted by a change of origin if the total charge does not vanish. And so this is an important point to remember as I move to more complicated topological objects in higher dimensions. So very briefly, the story that I'm going to talk about involves axion electrodynamics and condensed matter. So axion electrodynamics is a modified theory of electromagnetism in which you have magnetic monopoles additionally, and you also have this field, this theta field, which is called the axion field. And of all the new terms that you get, the one most relevant to this talk is the additional term in Lagrangian, where you have this magnetoelectric E dot B term that's proportional to the theta field. And so theta is the axion angle. It's defined mod 2 pi. And the values, 0 and pi, can be quantized by symmetries that flip E or B, but not E and B. So inversion or time reversal act to quantize theta. And it's also worth noting that, like the polarization, if you somehow have an axion domain wall, in the language of Wilczek, a 2D object for which delta theta equals pi, this object will bind a half-integer Chern state that's anomalous because it can't be realized unless on a domain wall or a boundary. And this sounds very exotic. Indeed, axions were proposed in a high-energy setting. They could be a candidate for dark matter. But bringing it closer to condensed matter physics, it was recognized that 3D topological insulators are actually axion insulators. They have a value in the bulk of theta pinned to pi, which can be contrasted with a vacuum, which effectively has theta equals 0. So the surfaces of 3D TIs are, in fact, axion domain walls. And so this leads to 3D TIs, if you can gap out all their surfaces and make a nice sample, in principle exhibiting a topological magnetoelectric effect, which was confirmed by Liang Wu and Peter Armitage in this paper. Now, additionally, it turns out that topological semimetals that are gapped to charge density waves can also have emergent theta fields. So briefly, what I mean by a topological semimetal is a 3D, for this purpose, is a 3D system where the Fermi surface, the system is almost gapped out, but there are a few points at the Fermi level that comprise the Fermi surface. And these nodal degeneracies can be protected by two mechanisms. You can have crossing bands with different crystal symmetry eigenvalues, like in a Dirac semimetal like cadmium arsenide. Or you can have something that's protected by like a topological invariant on some loop or sphere around it. And these ones, the ones where you have in particular the integral of the Berry curvature flux on a sphere being non-zero, are known as chiral fermions. The simplest ones with charge 1 are conventional Weyl points, but there also exist these unconventional ones with higher charge or higher degeneracy, such as the chiral multifold fermions that we predicted in cobalt silicide. And it's important to note that the surface projections of oppositely charged chiral fermions are spanned by surface Fermi arcs. These chiral crystal silicides were for that reason, well regarded because they have giant surface Bron zones spanning Fermi arcs. this gets us to the sort of main motivation for this talk and this area of investigation. So it was proposed that in a very simple Weyl semimetal, a magnetic Weyl semimetal with 2 Weyl points, if you link the Weyl points with a charge density wave that exactly matches them, you can backfold them and realize a 4-fold Dirac Hamiltonian with 2 mass terms. So it's a complex mass. So this is like complex numbers, this is real numbers, and you can imagine some winding. And so if you have a winding texture in the mass that corresponds in particular to a dislocation in this low energy theory, then you bind a chiral mode. And so the action associated with this theory is actually the same as the magnetoelectric action I showed before, or related to Lagrangian, but the coefficient is like the argument of the charge density wave, and in particular the phase angle sets the strength of the E dot B term in some limit. And so you could have like the phase angle in this picture acting like the theta angle in axion electrodynamics. And so this raises several questions. One, does this occur in real materials? 2, we now know a lot about magnetic band topology, and this is a K dot P model. It's not a lattice model. So is the bulk an axion insulator, or is it some other state if I were to take this model and lattice regularize it? And so we can answer both of these questions. So I'll sort of go in the historical order that it went. So if we want to find a material that has a charge instability, a good place to look are quasi-1D materials because they frequently host structural instabilities like the Peierls transition. And so from 2 different large-scale searches, we got hits for tantalum selenide iodide. First, by performing a high-throughput search using the method of topological quantum chemistry, we found that the quasi-1D material tantalum selenide iodide is an enforced semimetal at the Fermi level, and so that highlights there's some sort of crossing point here that's interesting. It's actually one of the only 2 materials. It's one of 2 materials in the whole topological materials database, a freely available online repository for searching topological materials. It's one of the only 2 materials with this crystal structure overall. So it's sort of an interesting tidbit, not necessarily related to this talk, but it's important to know that this is, as I'll get to, a chiral crystal structure. And so we are also looking at crystals that have a macroscopic or a geometric sense of chirality. They have a handedness. They can form in enantiomers. And for reasons shown in this paper, we showed that at high symmetry points, and even sometimes away from high symmetry points, all of the degeneracies in this complicated spaghetti should be chiral fermions in certain chiral crystals. And so for that reason, we pointed out that far away from the Fermi level, at least relative to this point, there are also chiral fermions below the Fermi level. So for these 2 reasons, this material seemed interesting to us. So we looked closer at it. And so we looked in the normal state, just looking at the DFT of the band structure. And so looking closer, tantalum selenide iodide is a structurally chiral quasi-1D material. The symmetries do not have roto-inversions, like inversion times C4 or C2, like a mirror, or inversion itself. And the crystal is made of very relatively weakly coupled 1D chains of tantalum and selenide. And the chains themselves have a near-perfect screw symmetry. It's actually a very fancy screw symmetry, this 8-fold screw symmetry that you could not get in a 3D crystal. So it's weakly broken by the interchain coupling. But there's also a 4-fold screw that results from this. And so for this reason, to leading order, the Fermi surface of this material is just entirely located at pi over c along the chain direction. Because you have a screw symmetry, and that makes to leading order a nodal plane right here. So this whole thing at k is equals pi over c is a plane. But if you allow interchain coupling and spin orbit coupling, this plane starts to wiggle a little bit. And in fact, if you do a symmetry analysis, there's nothing that can protect a nodal plane in 3D in this material, or nodal loops, because this material is symmorphic overall. It's backfolded into this I422 space group. And so for that reason, every time this thing wiggles, it forms a Weyl point. And so what we find is that from symmetry arguments alone, from knowing the space group and knowing that it's a metal or some semimetal in its normal state, it must be a Weyl semimetal. In fact, it must more generally say that every single crossing point in the entire spectrum has a chiral charge. And so focusing on the Fermi level, there's actually 48 Weyl points that form this very narrowly split nodal plane at kz equals pi over c. And so they look really bunched up on the side view. But if you were to be able to look from the top, they have a little bit more spread. They're a little bit more localized near kx, ky equals 0 and kx, ky equals pi. So these materials, because they're quasi-1D, they like to grow in needles, and you can cleave them, but sort of on the side of the needle, on the 1,1,0 surface. And as I mentioned, the Weyl points are extremely narrowly separated in Kz. They have a little bit of more spread in Kx and Ky, but it's still hard to see. And so the surface Fermi arcs are expected to be quite narrow. There were some APS experiments, and they show a little bit of high charge density where the Fermi arc should be. This picture is rotated in this paper, so the axes, unfortunately, are 90-degree rotation of our axes. But this region you might imagine corresponds to these Fermi arcs, and this region corresponds to these Fermi arcs. But because of this, as well as the fact that this calculation doesn't have any broadening effects, this is some simulating very low temperature. It's unlikely that you're going to be able to resolve the surface Fermi arcs without having a fantastic series set up or something beyond what is currently being done. Now, it's important to point out that if you could somehow chop off the top surface of this material, you would see surface boron zone spanning Fermi arcs. They would go all the way from kx equals 0 to kx equals pi, and this whole bunch has a net charge of 8, and this whole bunch has a net charge of -8. So this is actually sort of the highest grouping of chiral charge that's been seen in a material or predicted, and it's extremely similar, just with higher symmetry, to what was predicted in the cobalt silicide family. Tantalum selenide iodide is already known to host a charge density wave phase, and it's known that it's gapped. The phase can be accessed just below room temperature, and so we performed, Holger Meyerheim performed X-ray diffraction experiments. In our samples, we found that the charge density wave phase has this symmetry with 3 two-fold rotations, 2, 2, 2. It has two-fold rotation about the z-axis and two-fold rotation about the x plus y and x minus y axes. The pattern that you see has spots that are related by C4 symmetry, but they have different intensities. So we interpret that to say that the fourfold symmetry of the normal state is broken, and that there's domains throughout the sample with different volumes in which that order is broken differently. So the CDW is almost 1D, it's almost pyrals, but there is an in-plane component that corresponds to very weak interchain breathing. And that's important because Weyl points are 3D objects and you'd want them to be gapped out by something like this for this to make sense. And so the point is that this is a 3D Weyl semimetal. The charge density wave is almost 1D, but there are 3D corrections to it that lead to dispersion in plane. And so overall, we find the charge density wave to be 3-dimensional. So performing ARPAS experiments and looking back on older transport experiments, the CDW phase is gapped. It's definitely gapped. However, the wave vectors are much, much smaller than the Weyl point separation vectors. We further performed electronic susceptibility calculation, and the hotspots in that, which you might imagine to be the regions contributing to the charge part of the CDW instability, are also much farther than the experimentally observed wave vectors. Nevertheless, you could look at all the Weyl points, and you could express their separation as integer multiples of these tiny, tiny wave vectors with an uncertainty. And it's also important to point out that we don't need the CDW to be perturbatively weak. I mean, this gap is much bigger than this gap, the Weyl point separation in the plane. So even if they miss by a little bit, the strength of the CDW order is certainly going to make up for that and gap them out. And so overall, whether or not you agree on what the exact wave vectors are, I think most people would agree that it's a chiral crystal structure and that it's gapless above room temperature. And so for those reasons alone, its tantalum selenide iodide must be a Weyl semimetal in its normal state. And because the charge density wave is gapped, it must be a material in which the Weyl points have become linked and gapped in some manner by a charge density wave. Now, so for the last 10 minutes, I want to briefly build up to some questions that this may raise. So tantalum selenide iodide has many, many Weyl points, and it's not a magnetic Weyl semimetal like the original proposal. It's a time reversal invariant Weyl semimetal. So this is a little bit different than the original proposal, and so how do I understand the response of this? So there's several ways in which we can build up to this. First, there's a question of if I were to, as I mentioned before, lattice regularize, or the original Weyl charge density wave model, what is the band topology of that model? And so that can be answered through these methods below, magnetic topological quantum chemistry, and what are known as Wilson loops and non-abelian Berry phase, as well as computing the Hall conductance of slabs of models, and also this theoretical method popularized by Zita Song and others of the layer construction method for understanding symmetry-protected phases of matter. So we're going to use this analysis to analyze magnetic, simple Weyl semi-metal charge density waves, and then Dirac and Weyl charge density waves with an additional doubling due to time reversal symmetry. So as an introduction, if I just have inversion symmetry and lattice translation in 3D, then there's what are known as symmetry-based indicators that give you a partial classification of the topological phases. There's a strong Z4 invariant, and there's weak Z2 invariants. And the weak Z2 invariants correspond to, in K-space, the Chern number in the K equals I plane, mod 2, and the strong invariant can tell you a little bit about the axion angle in cases in which the bulk is gapped. And so the prototypical way to think of this is by building up by putting layers of Chern insulators, 2D Chern insulators in the 3D unit cell, and having them pinned to some position with a symmetry. So in a 3D quantum anomalous Hall state, you can have a Chern 1 layer at Z equals 0, and this corresponds to having actually these symmetry indicators, 2, 0, 0, 1, and so you have a Chern number that's 1 in Kz equals 0 and a Kz equals pi. Now this could be contrasted with a static axion insulator, which is like a 3D TI with inversion symmetry and then time reversal broken. So here you have alternating layers of Chern equals 1, Chern equals minus 1, pinned to 0.5 by inversion, and this phase has theta equals pi in the whole bulk. And so this, again, this theta being the coefficient of the magnetoelectric Lagrangian. So what we're going to do is we take a Weyl semi-metal with 2 Weyl points in inversion symmetry, and we link them by a charge density wave, and we gap out the system, and we compute the theta angle using the methods that we talked about previously. So what happens is the Weyl points become backfolded. You get a 4-fold Dirac point, and it can gap one of 2 ways that keep inversion, as leading to these circled parity eigenvalues. So on the left, I have a 3D quantum anomalous Hall state that I get by gapping them out with negative eigenvalues. And on the right, I have another 3D quantum anomalous Hall state, just with different parity eigenvalues. Now, these states both have the same Chern numbers, but they have different symmetry-based indicators. So one might ask, what does this 2 mean? Well, it turns out that you can compute the axion angle in systems where the total Chern number does not vanish. You can actually express it either way as a sort of Chern number polarization. So if I look along this direction, I just sum up the Chern numbers of layers times their position. And much like the charge polarization, if the total Chern number doesn't vanish, then I'm certainly able to get non-zero values for theta, but they're origin dependent. So here, this phase of matter, the quantum anomalous Hall state on the left, is just related to the quantum anomalous Hall state on the right by a fractional translation. You and I will disagree on which one has theta equals pi. However, they are still topologically distinct quantum anomalous Hall states because domain walls between them differ by an axion insulator. If I take the subtraction of these 2 states, I get a static axion insulator, and so domain walls between them are still topologically meaningful. And so this tells you that in the original proposals, I don't have axion insulators. I have quantum anomalous Hall states, but I can understand it very physically. In the charge density wave state, the phase angle corresponds to the region in real space where the layer lives, which is like the region of high charge density. And I can advance that layer by making phi, the phase angle, go from 0 to pi. And that also moves the axion angle, the origin-dependent axion angle, from theta equals 0 to theta equals pi. And in these models, because they're, these states, because they're quantum anomalous Hall states, a dislocation binds a chiral mode, which we'd expect from the axion string prediction in the original papers. So what happens if I restore time reversal symmetry? Well, in time reversal symmetric systems with inversion, you have the same symmetry indicator group. You have a Z4 for the strong index, and you use Z2s for the weak indices. But the weak indices here correspond to planes in real space having a non-trivial Z2 invariance, and the Z4 corresponds to strong or higher order topological insulators. So the prototypical layer construction on the left is a weak TI with one layer of a Z2 TI per unit cell. And on the right, you have an archetypal helical higher order TI with two layers of 2D TIs per unit cell pinned by inversion. Now, importantly, this phase, being equivalent to two 3D TIs or two axion insulators superposed, has a net trivial theta angle. So what happens if I take all the Weyl points, or more Weyl points, or Dirac points with time reversal and inversion symmetry and link them with a charge density wave? Well, if I do this, I get a doubling of everything I talked about previously. First, I'm backfolding 4 two-fold degeneracies or 2 four-fold degeneracies to the same point. So the quantum critical point that describes this phase is in fact an 8-fold double Dirac fermion of the kind that we predicted in this work in 2016. And so in this work, we expected there to be helical mode dislocations. And in fact, are helical modes along 1D mass defects. And what we'll see below is that that's in fact consistent with this model. So in the charge density wave state, there are, again, a phase angle. And again, I get a kind of weak phase, not a strong phase. I can gap out the 8-fold Dirac cone to have the parity eigenvalues here, leading to a weak TI phase with a layer at 0. Or I can gap out the 8-fold Dirac cone like this in the charge density wave state and realize a layer at pi, or is z equals a half. And these are two weak TIs. They differ by a half translation, but they also differ by symmetry-based indicators. And so we know they're topologically distinct, but they both have the same trivial theta angle. So they differ by a helical higher order TI, but because the helical higher order TI has a trivial theta angle, I can't say anything at this level about domain walls in these phases. But what I can say is because it's a weak TI, a dislocation definitely binds a helical mode. So in this sense, this is like maybe a Dirac string. It's a doubling of the axion string in the previous models. So what I can say now, very briefly, is a little bit more on this. So to conclude, in the last year, we've done a lot of research on this model where you have a trivial theta angle, but you clearly have some topology. And so the point is, even though theta is trivial, there exist limits in which there are emergent sector degrees of freedom from doubling everything. And you can define in a gauge invariant sense theta per sector and realize a kind of what are known as mutual axion electrodynamics. So here, the E and B fields are the real fields, and the other E and B fields are emergent fields. And what I mean by that is, in a situation in which you sort of have an orbital character to the doubling, you can get an emergent Valley degree of freedom. And so in this paper, we looked at the limit where you induce magnetism from dynamical strain. So these these fields become pseudoelectric and pseudomagnetic fields that emerge from strain and torsion. But in a static helical higher order TI, you can also have a kind of mutual axion electrodynamics where the S field is spin. So you have new spin magnetoelectric responses, which we're going to point out, which we hope to announce very shortly in these papers that are making their way through various stages of completion and submission. Also, there are some talks on the spin version of this here that were given yesterday, at least one of which is online. To conclude and summarize, the simplest Weyl semimetal gap to the charge density wave can be understood to be as 3D generalizations of the original Su-Schrieffer-Heeger model of polyacetylene. This can be done by making a connection to the layer construction and topological quantum chemistry theoretical methods. And the upshot is that 2D domain walls in either the axion angle or the partial axion angle bind some kind of soliton. And those solitons are either half quantum Hall states or something new, a half quantum spin Hall state, as we're going to point out in this paper. And so in some sense, these axion domain walls were known for a long time. Even in the original paper by Frank Wilczek, something I didn't appreciate till recently is that this whole model is in fact in 3D. So these domain walls are 2D soliton-like objects. Tantalum selenide iodide is a material that we identified. It's a very complicated quasi-1D Weyl charge density wave. I covered that up. Now it's shown some magnetoresistance signatures at in-gap 1D states observed that are consistent with this prediction. And And on that, I would like to comment that there's some wonderful data to that end in talks and in some of these papers and this talk by Zahid Hassan's group. But so, for example, for the in-gap states, there are experiments where you see them, and there are experiments where you don't. And so the Fermi surface is extremely complicated, and the Weyl point coupling details may be very sensitive to sample preparation details. And so what one should say in general is that the overall response that you see might depend on the details and the sample quality. So I would also point out we have an upcoming work where we have relatively simplified models of the charge density wave state. And even in those models, there's competing competition between different ways to gap out this state, which lead to different physical observables of the topology in the charge density wave state. So these are my collaborators. I want to thank all of them, and thank you for listening.
Great. Thanks for the nice talk, Ben. Are there any questions? I can actually start out with a question.
Yeah.
Which is, for the charge density wave in Weyl semimetals, there's a phase angle, but that phase angle is not pinned by anything, right?
Unless you have a symmetry.
So will that correspond to a non-quantized axion response?
Yeah, it's a dynamical axion angle. So you could say that, like, if the whole sample had a fixed phase angle that was random, then you would get a non-quantized axion response. But also, if you could make it like wobble with some external field, then you could measure some dynamical axion. So there's some other parallel work on these systems with emergent theta fields but unpinned theta fields. Yeah.
Got it. Any other questions? Yes, there's questions from the virtual audience. So the first question is, what is the physical origin of the charge density wave instability connecting the two Weyl points?
It doesn't matter. If they go along for the ride, whether it's them, some correlation between them, or whether phonons, it doesn't matter, because what we've shown is that even in the mean field, the band topology of the gap state has some axionic character to it.
So are you worried that since the density of states at the Weyl points is 0, that there's not an instability that you would expect?
No, because as I mentioned, Fermi surface nesting is not usually the origin of 3D charge density waves.
Okay. In-person question? Go for it.
Hi, Ben. Great to hear what you're up to. This was really fantastic. When you talked about the topological phases, you made clear that the way to establish them is by looking at interfaces between different variants. I think that's always a strong statement. When you look at the axions, you said in some cases that the axion behavior would come at a domain wall as well. Is that always the case, or are some of the materials exhibiting axion electrodynamics in the bulk, in a sense?
So what I would say is there's two classes of materials that, maybe it's a two-part thing. I would say if the theta angle is pinned in the bulk, like in a 3D TI, then there's still a domain wall. It's the surface. And in some of these other materials, it varies depending on the details of the phase angle in the charge density wave in some region. And so domain walls also correspond to that physics. And so you could really think of some picture where if I'm allowed to have solitons, I sort of think that I forget the field and I just look at the configurations of domain walls and solitons and how they would slide if I depin them. So, and that has to do with the fact that this object that I showed, this Chern-Simons angle, is some total derivative, so that what matters is sort of on the boundary instead of in the bulk.
Okay, thank you for that.
Yeah.
I'm going to ask a question from the virtual audience, which is, suppose that you adiabatically turn off the small spin-orbit coupling in the charge density wave phase. Do you think that the physical properties will change qualitatively?
No, because it's still a chiral crystal. It still has chiral fermions. If you look at the band structure without spin-orbit coupling, there's a tab on our website to do that. We might have put it in the paper as well. And of course, the spin-orbit coupling has a small effect on the band structure.
Great. Question?
Thank you for the great talk, Ben. So is there any expected physical phenomena we can see from amplitude mode instead of the phase mode?
Off the top of my head, I don't think we considered it, and I haven't thought of that before. So that's something where you're saying like the what's it called? This delta varies, and yeah. So with modulation and delta, I mean, you would see if there's some region where delta was 0, you might see a gapless state because it's a semi-metal. So depending on the period of it, maybe you could resolve that. There's a gaplessness that somehow corresponds to something left over from a topological semi-metal, but I haven't seen it or analyzed it theoretically myself.
Okay, thank you.
Yeah.
Okay, I'm going to ask one last very quick question from the virtual audience, which is the charge density wave driven by nesting between Weyl points or electron-phonon coupling? Do you have any comment on that? Or?
I did address that previously. There's papers that look at the phonon origin of it. They see phonon modes that would probably contribute to it. So I would say, coupled with our calculation of the electronic susceptibility and the spots you see there, surely phonons play a role.
Mm-hmm. Yeah. Great. All right. Thanks again, Ben, for an excellent talk.